Hello physics students. So in the last physics video, I showed you how to derive the formula for the capacitance of a parallel plate capacitor. And what do I mean by a parallel plate capacitor? Well, basically these two sheets of paper model a parallel plate capacitor. We have one sheet of metal here, one sheet of metal next to it, straight parallel, closer together than this. And of course, you ignore this block of wood on the top. That's just makes it convenient for me to hold these up at the same time. The formula is epsilon 0 times the area of one of these plates, not both of them, just one, divided by the distance between the two plates. And of course, these plates need to be close enough together so that they can be approximated as infinite in size for the dimensions involved. Today what we're going to do is figure out how that capacitance changes if you take a metal slab of some thickness and you insert it between these two plates, okay? So, and you can put it maybe right in the middle, or maybe you can put it closer to one side or the other. We're going to find that where you put this in between the plates doesn't matter. If it's closer to one side or the other, it changes the capacitance by the same value. In fact, we're going to see that it increases the capacitance. And so we're going to derive a formula to show how much it increases it by. That's the topic for today, putting a slab into a parallel plate capacitor. So I've sort of schematically sketched what was going on, what I just showed you. Here, this is the original capacitor, some distance d apart, and this is what its capacitance would be. Then I put a metal slab of some thickness. I use the symbol A because I already used D over here. And so let's say that this is some arbitrary distance x away from one of the plates. Then of course this is the total D minus x minus A will give us this little space right here. We want to know what the capacitance is. So what we first have to realize is that this can be thought of as now two capacitors. Because this block of metal is like a conductor, we could actually hollow it out and just put a wire connecting the very thin edge over here and thin edge over here, and it would schematically, or it would functionally behave the same exact way. So it's really two capacitors, one here, and then we could use this formula for each of the capacitors because they're simple parallel plate capacitors, epsilon 0 A instead of D, the distance x between these plates, and then here the same formula, instead of D, the distance between those plates. So I'll pause and give you a chance to copy these notes down if you haven't already. Okay, so now what we're going to do is get the total capacitance by realizing that these two capacitors, which are really this, are two capacitors in series, not in parallel. So what we have to use is the rule for adding capacitors in series, which is right here, that reciprocal rule that we learned a couple videos ago. So what I'm going to do is just go ahead and instead of putting this capacitance right here in the denominator, I'm going to go ahead and do the reciprocal right away. So I flip it over, put it right there. And same with that one. And now you see, conveniently, they already have a common denominator, epsilon 0A. So the x here and the minus x cancel, leaving us d minus a over that common denominator, which we flip over and we get the new capacitance. And as I wrote here, note that the position of this slab doesn't matter. X is not in the formula. So I could have this very close over here and a big gap down here, or right in the middle, or the other way. So X coordinate doesn't matter. And then final thing that I'm going to do is see how that relates to the old capacitance. All right, we could already see that it's going to be greater because the denominator just got smaller by the factor of A. So more capacitance. But how much, what fraction greater compared to the old? So what I could do is I could multiply this formula by d over d, which basically I'm not changing it. And I did a little color coordinating here because now I could lump this and this as my original capacitance that I had over here before the slab was inserted. And now what I have is the d over d minus a, which is some fraction greater than 1, right? Because this denominator is going to be smaller. So it's maybe like 1.5 times the original or 1.7 times the original, depending on what this comes out to be. So there it is, the new capacitance. if you haven't already, I'm going to pause and give you a chance to catch up with the notes. Okay, well, the next thing that we're going to do is we're going to see how when we put the slab in, as we're putting it in, what's changing in a capacitor in terms of its charge, its electric field, its voltage, and also the energy that's stored in the capacitor. And so there are two possibilities, just like in the last video that we saw, that you watched. One is the capacitor is isolated. We charge it up. And then isolating means we disconnect it from everything. And then we put the slab in. How do all those factors change? The other scenario we're going to look at is what happens if the capacitor stays connected to a battery the whole time, and then we put the slab in. How does charge, voltage, electric field, all those things change? So that's what we're going to do is case one. Capacitor is isolated. So this is before. And then maybe we've got plus Q here and minus Q here, and we're going to put zeros here because they're the original. And then after, what happens when we put that slab in, okay? And of course, we're inserting it in there, okay? So the first thing that we know is now the capacitance has increased by that factor. We already derived that. So capacitance goes up, okay? Might be needing a new marker. But another thing that we know is that the charge does not change. How do we know that the charge doesn't change? We said the capacitor was isolated. If we put the charge here, there's nowhere for it to escape to or nowhere for more charge to come from some other source. The electric field, therefore, also does not change. And how do we know that? Well, remember, E equals sigma over epsilon 0 around an infinite plate of charge. And so if we haven't changed the charge here, we'd create a little Gaussian surface, we do Gauss's law calculus, nothing's going to change. So same charge, same sigma, same electric field, okay? However, the voltage this time does decrease. Why? Well, let me just write the expression. How do I know that? Well, from this expression, that voltage, maybe I'll write this a little smaller. Okay. V equals ED. So, what I'm doing when I insert this slab, remember it's a metal, a conductor, and the electric field inside a conductor is 0. So if I integrate the electric field starting from here to here, I integrate and I accumulate voltage here, and then I don't accumulate any as I'm integrating here, and then I accumulate more voltage here. So I'm only accumulating voltage in these regions before I accumulated the whole way. So the voltage, therefore, got smaller. Now, the other thing, now that we know the charge is the same and the voltage went down, we can conclude that the energy in the capacitor is now also smaller. And it's smaller by that D minus A over D factor. How do I know that? Well, remember this formula. The energy in a capacitor is 1/2 QV. And so with the same charge but less voltage, I have less energy in the capacitor. And now the question is, well, where did this energy go? Energy can't be created or destroyed. Suddenly we have less. Where it went to is, if you think about this, if this is, say, positive and this is negative, what's going to happen is this is going to induce a charge where the top of the metal is negative and the bottom of the metal is positive, because the electrons in the metal here are going to be repelled upward or attracted upward. Either way you look at it, they're going to end up near the top of this metal plate. And now if you think about forces, this is attracted this way and this is attracted this way as it's coming in. And so this then has a net force inward. The slab has work done on it. It's pulled in, and maybe it gets velocity, kinetic energy in the process. So the energy that's, quote, lost went to work on the slab. And so that's where that energy went, okay? We're going to do the same analysis, but this time with the capacitor not isolated, but connected to a battery. So before, oh, by the way, I don't know if I created a pause, so let me go ahead and do that now in case I didn't. Okay, so before, what we have is a capacitor like this, and it's got plus Q0 and minus Q0, and it's connected to a battery here. Voltage 0. And then, maybe I'll circle this. Then after, what I have, my capacitor like this, slab in here, and the same battery. So once again, what we can conclude is the capacitance, first of all, increased. Because again, capacitance doesn't matter whether you're hooked to a battery or not. It depends only on the geometry of a particular metal configuration. And so the battery or no battery, still the same capacitance because it's just this. Now, the other fact that's true is the voltage does not change when you insert the slab, because the battery maintained the voltage, okay? Now, if the voltage remains the same, what we know now is that the electric field this time must increase. Here it stayed the same because the charge stayed the same, but here, remember, the voltage when you integrate is only from here to here, right? So along these, so with less distance over which that electric field can exist, because E here is 0, with less distance you need more electric field to accumulate the same voltage. So the electric field increased by this. And again, as I said, from V equals ED, we reason out. Stays the same, got smaller. This must have gotten bigger. Okay? Now, therefore, the charge now had to have increased because the electric field increased. How do we know that? Once again, if the charge increased, and we know from Gauss's law, the electric field is sigma over epsilon 0 inside of a capacitor. And so with more electric field, as we already reasoned out here, we need more sigma, and therefore there's more charge on the plates. And the last thing, energy. Well, if we have the same volts, but now we have more charge for the same volts, we can conclude that the energy went up in this case. U equals that factor increase in the energy. And how do we reason that out? Well, we reason that, again, like over here, that electrical energy is 1/2 QV. And so, with the same volts, because the battery maintains the same voltage, but with more charge, there is now more energy in the capacitor. The question is, energy cannot be created or destroyed. There's more energy. Where did it come from? Well, it came from the battery. The battery pumped on more charge, and when a charge comes out of the battery's discharging, losing energy. That energy went into the capacitor. So energy came from the capacitor. I mean, from battery. All right, if you need a moment to catch up, I'll create a pause to allow you to catch up. Okay, so that's it for today. We determined that when you put a slab inside between two parallel plates, a metal slab, it makes the capacitance go up. We were able to derive an expression to show how much it went up by. And there's a little fraction involved there with the thickness of the slab. So that you need to be able to do. And then also you have to also know how the charge, the voltage, the capacitance, the electric field, and the energy change when you put a slab in. Case 1, the capacitor is isolated, then all these expressions are true. Case 2, the capacitor is connected to a battery and the battery maintains the voltage. What happens to all the factors? All right, so I hope you enjoyed this physics video. I'll see you in the next physics video.